Hello, today we're going to finish Chapter 5 and continue our discussion on stereoisomers. In the last section we left off right before optical activity. We described a lot of the differences between enantiomers and how to tell them apart, how to determine if we have R versus S. What we're going to look at now is some of the physical properties that enantiomers have with relation to each other. So you can see here we have two natural product small molecules. These are R-carbone and S-carbone. These are two enantiomers of each other that are both found in nature. And one of the things you'll notice is that these molecules have the same physical properties. So all enantiomers are going to have the same physical properties as one another. Stuff like melting point, boiling point, polarity are going to be exactly the same. There are going to be two major differences that the R enantiomer will have relative to the S enantiomer, and that's going to be how they interact with other chiral compounds. So the R enantiomer might react differently than the S enantiomer with another chiral compound. And then the second difference will be their optical activity. The enantiomers are going to have the opposite rotation of plane polarized light. And in order to discuss that, we'll first have to discuss what plane polarized light is. So if we take all the light, all the waves of light, they're going to be completely random. We can use a filter to orient all of the light so as it travels through a filter, it will be plane polarized. And then based on the compound that we have, the light might have a slight deviation to it. So enantiomerically excessive compounds, when you have more of one enantiomer compared to the other, are going to actually rotate this light. So if you look here, we have a light source, and we have a polarizer, and then a tube. And if we fill the tube with the molecules, as the light shines through from the source, it's going to all orient in one direction using the polarizer. And as it passes through the molecules, they will rotate the direction that the light is traveling. So the emerging light is not going to be the same as the light before it entered the polarimeter tube. And depending on the direction that the light changes, we can learn some information about the enantiomer. So enantiomers will rotate the plane of the light to an equal degree but in opposite directions. So if we go back to this tube, right? If we start at 0, which is how the light entered the tube, one enantiomer would rotate it to the right, positive degree sign, and one would rotate it to the left. If there was an equal mixture of the two enantiomers, a 50-50 mixture of the two enantiomers, then we would observe a 0 degree shift in the light. There's a few parameters that we have to incorporate into an equation that calculates the specific rotation. And the specific rotation for each compound is going to be specific to that enantiomer. And so we're going to look at the observed rotation, and that is going to be related by also the concentration of the molecule and the path length of the solution. So if we use, for example, 1 milliliter solution and we use 1 dm path length and 1 gram of compound, we can kind of have some standard amounts for this specific rotation calculation. And we also have to take into account the temperature of the solution. So these are all parameters that will be used for the calculation of optical activity. So let's consider the enantiomer of 2-bromobutane. So at 20 degrees, our 2-bromobutane will rotate the light negative 23.1 degrees. And, negative 23.1, it's unitless. And the S-bromobutane will rotate it positive 23.1. So you could see the two enantiomers rotate the plane polarized light an equal amount, but in the opposite direction. The R and S configuration refer to the stereochemistry at the center. And we have another notation that we're going to look at, which is a positive or a negative, and that's going to refer to the direction which the plane light is rotated. So positive would be dextrorotary, and negative is levorotary. And these are going to be completely unrelated to whether we have an RRS stereo center. So there's no correlation at all between the stereo center being RRS and if it's dextro or levo. That's the direction which it will turn the light. So this is going to give us some information about the molecule. We can't necessarily predict the magnitude and direction of the optical rotation from looking at the structure, but if somebody else has already isolated this molecule and studied it, this information would be known in the literature. And so you could look up the literature value, for example, for R carbone and see specifically under a set of conditions, a solvent, a temperature, a path length, what the measured optical rotation was from those scientists. If we have a mixture that's a 50-50 mixture of the two enantiomers, this is going to be called a racemic mixture. So a racemic mixture, this is an important key vocabulary term. A racemic mixture is a 50-50 mixture of two enantiomers. What do you expect that the optical rotation would be for a racemic mixture? There would be no optical rotation, right? It would be at 0 because we have an equal mixture of the two. If one of the enantiomers is present in excess, so for example a 60-40 mixture, then we're going to have an unequal amount of the two enantiomers, and it'll affect the optical rotation. So because there's more of one than the other, it'll either pull the optical rotation to be positive or negative. For example, if we look at these two molecules, what if we know a pure R sample and a pure S sample have these two values? What if we have a specific rotation of 4.6 degrees? Then we are actually going to be able to calculate the ratio of the two compounds, because we know 100% pure would rotate it to 23.1. So this compound must be in excess, and we can use this equation to calculate in how far excess. So that's taking the observed specific rotation and dividing it by the rotation of the pure enantiomer. So for this case, it would be the negative 4.6 divided by negative 23.1 gives us a 20% enantiomer excess. So that means we would have a 60-40 ratio of the two enantiomers, because one of them is 20% excess to the other. So just to kind of summarize where we're at until this point, we have isomers, and we were able to break those down into two categories. We have constitutional isomers, and we have different connectivity, right? Different sigma bonding framework. And we have stereoisomers, which have the same connectivity, but they're non-superimposable. Within this category, we have two subcategories. We have enantiomers. These are stereoisomers that are mirror images of each other. And we have diastereomers, which are stereoisomers that are not mirror images of each other. Often diastereomers are going to have multiple stereocenters, but there's another example of diastereomers. Let's look at cis versus transbutene. These molecules have the same atom-to-atom connectivity, so they're not constitutional isomers, but they are not mirror images of each other. Therefore, they must be diastereomers. Enantiomers have identical physical properties from each other. Same boiling point, same melting point, same polarity. However, diastereomers are going to have different physical properties from each other. So the cis versus transbutene might have different melting or boiling points, for example. So let's consider a cyclohexane with 3 substituents. We have 3 chiral centers, right? Each of these carbons has 4 different substituents attached to it. And so because we have 3 stereocenters, we could designate them all, right? This one could be R, this one could be R, this one could be S. The mirror image of this molecule found here, or its enantiomer, is going to be the exact opposite stereocenter at all three positions. So these are a pair of enantiomers. What about this molecule? What's this molecule's relationship to these molecules? Well, it's no longer a mirror image, right? Because we've only moved one stereocenter. So these are diastereomers of each other. The relationship between these two molecules, though, are enantiomers, right? We have R, 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 and we have S, S, S. So we have a pair of enantiomers. These two enantiomers are diastereomers of these molecules. And you can see all of the 8 possible orientations of stereocenters are found here, and they're separated into 4 pairs of enantiomers. These, inside each green box, the molecules are an enantiomer pair that are mirror images of each other, and the stereocenters completely flip for both molecules. The total number of stereoisomers for a compound is going to follow the formula 2 to the n, where n is the number of chiral centers. So, for example, looking at this molecule, how many possible isomers would we expect? We first have to count the number of stereocenters, right? So we have 1, 2, 3, 4, 5, 6, 7, 8 stereocenters. So we would expect the total number of stereoisomers to be 2 to the 8th. So any compound with only one chiral center will be a chiral compound. In some cases, if we have more than one chiral center, we might have a plane of symmetry inside the molecule. For example, these two molecules, the trans 1,2-dimethylcyclohexane does not have a plane of symmetry. The cis does have a plane of symmetry. The trans molecule is going to be chiral, and the cis isomer is not going to be chiral. If it has an internal plane of symmetry, like the cis does, then it is not chiral. Because if we took the mirror image of this molecule, they would be superimposable with each other. So looking at the chirality of a molecule, or the presence of an internal plane of symmetry, is going to be important when we go to identify if a molecule is chiral or achiral. The molecules which have an even number of chiral centers and a plane of symmetry, like the cis cyclohexane that we found here, are called meso compounds. There's 2 methods to tell if a compound is meso. One is to identify an internal plane of symmetry, or the other is to take the molecule, draw its mirror image, and then try to superimpose the two. If a molecule is identical to its mirror image, then it is not going to be chiral by definition. So if a molecule has a plane of symmetry, it is achiral. If it does not have a plane of symmetry, there are a few other modes of symmetry that might exist. It could still be achiral if it has an inversion point. So if we take this molecule, and this is kind of tricky to see, but if we take this molecule, right in the center there's an inversion point within the molecule. This is another mode of symmetry. And we can see this also with the fluorines, right? If we were to take this molecule and do an inversion, the yellow F goes to the pink, the teal goes to the green, and the blue and orange swap. So that same would hold true to here. For this molecule, it would have a inversion point within the center of the molecule. So overall, the presence or absence of rotational symmetry is irrelevant to chirality. We could have a plane of symmetry in a molecule, and that makes it achiral. And if it does not have a plane of symmetry, it's usually chiral unless there's an inversion center. Some of these exceptions. And that inversion center is generally pretty rare. There's not many molecules that would have that inversion center. A compound that's achiral because of symmetry is called a meso compound. So here are some examples, right? The cyclohexane with the 2 alcohols that are cis, There's a line of symmetry, a plane of symmetry through the middle, plane of symmetry through the middle. Here we have a plane of symmetry. And so meso compounds are going to have less than the predicted number of stereoisomers because some of these stereoisomers are going to be identical. So some practice for the worksheet to identify how many unique carbons the following molecules have. Think about the symmetry of each of the molecules. If you think about the symmetry, it makes it much easier to answer the question of how many unique carbons exist. And we'll do some practice problems with this. So another method that we have to represent to use a two-dimensional representation for a three-dimensional structure is the Fischer projection. In the Fischer projection, we're going to have a horizontal line representing the parts of the molecule that are coming towards us out of the page, and we're going to have the vertical lines representing the part of the molecule that are going into the page. And this allows us to analyze molecules that have multiple stereocenters very quickly. So for example, we can have 2, 3, and 4 chiral centers represented with Fischer projections. And we can use this information to rapidly assess the type of relationship for these stereoisomers. For example, on the left here, the Fischer projections are mirror images of each other, and these molecules will be a pair of enantiomers. Each stereocenter is inverted. However, on the right structure, the top stereocenter is going to remain the same while the bottom stereocenter inverts. So these molecules would be diastereomers of each other. Their Fischer projections are not mirror images. When we were looking at the conformations in Chapter 4, we discussed how we can rotate around single bonds. So while conformations themselves are chiral and enantiomeric, these rotamers are going to be able to rapidly interchange by bond rotation. So the butane itself is not a chiral compound. So for example, these two conformations of butane would be chiral relationship, but since this equilibrium is so quick and it can rapidly convert between all the different conformations, the molecule itself will be a achiral compound. For example, let's look at this, the chair conformation. So here's the chair conformation of cis 1,2-dimethyl cyclohexane, and the conformation itself are chiral and enantiomeric, but because we can ring flip back and forth between the two conformations very quickly, and we have a internal plane of symmetry in the molecule. Overall, this is going to be an achiral compound. There are some molecules, though, that are locked into a single conformation, and these are called atrop isomers, and these are stereoisomers that would be interchangeable through a rotation of a sigma bond, but the bond is unable to rotate. So for example, in binap here, this molecule, if you look at this bond, it's a sigma bond, so we would expect free rotation to be able to occur. However, these phosphorus atoms have 2 phenyls attached, which are extremely bulky groups. And that prevents, through sterics, it prevents free rotation. So based on which conformation the molecule is locked in, we're either going to have R binap or S binap. This is considered to be an axis of chirality. So we don't have any chiral centers with this molecule, but we do have an axis of chirality. Another example that's a little bit another example of chirality that doesn't involve a chiral center is this molecule allene. And we've looked at this molecule in class. We discussed that this carbon is sp hybridized because it's making multiple pi bonds with 2 different carbons. And if we look at those orbitals in 3 dimensions, you can see here's one set of p orbitals, and orthogonal to it, we have the other set of p orbitals. If we have different groups at the end of an allene, then we're going to have chiral compound. because the mirror image of these two molecules will not be superimposable. So it depends all on the substituents. Most methods that we use to separate different molecules, and we've gone through these in lab, are going to take advantage of the physical properties of the molecule. So it's actually quite difficult for us to separate enantiomers from each other. There are a couple different ways that we typically would separate the molecules, like distillation or recrystallization. But often these won't work to separate one enantiomer from each other because they have identical physical properties. The one property that we discussed earlier that enantiomers or chiral molecules will have different from its enantiomer is the way it's going to interact with other chiral molecules. So, for example, the first resolution or separation of enantiomers, so resolution is a term we use for separation of enantiomers, was done by Pasteur for tartaric acid. And he actually was able to do this with tweezers because the crystals that they formed were different. But this was a very rare case for these molecules, and it's not common that you'll be able to actually physically separate the molecules from each other based on their crystals. Another method is to create a pair of diastereomers. So we could take a chiral molecule, and we could take a chiral resolving agent. So this molecule has one stereocenter, and its enantiomer has one stereocenter. So we take the pair of enantiomers, and we combine them with a different molecule that has a stereocenter. Now we formed two diastereomers. And diastereomers have different physical properties, so we can separate these now. So because each of these molecules is interacting differently with this chiral molecule to form a diastereomeric pair, or salt, we're able to physically separate them at a later time. There's also a chromatography method using a column that's going to have some sort of chiral solid phase to it. A chiral absorbent is used, and the enantiomers will act with the column differently, and they will leave the column at different rates. So this is probably the most common way of separating enantiomers. In some cases, we're going to have an alkene or double bond that has more than two substituents. And in this case, we're going to use the E or Z notation instead of cis or trans because it's not adequate to differentiate between the two diastereomers. Cis and trans only works if there's a like group on each carbon of the alkene, but here we have different groups, and so we'll have to prioritize actually the groups using a similar priority method that we used in the past by atomic number. So we prioritize F as the number 1 and N as the number 2, carbon is the number 3, and hydrogen is the number 4. But we really just care about the first two priorities. So this would be a Z because we have the first two priorities on the same side of the double dot bond. And that Z stands for Zusammen, which means together. So the priority 1 and 2 are Zusammen, or together. If the top priority groups are on opposite sides of the double bond or antigen, that means the opposite side. So these are the notation we're going to use for determining the stereochemistry of an alkene with multiple different groups. So just to kind of summarize, if we have all of the molecules, we can separate them into two categories. Molecules that are chiral, these are molecules that exist as a pair of enantiomers, and we have molecules that are achiral or do not exist as a pair of enantiomers, or they possess an internal mirror plane. Examples: enantiomers, we change both stereocenter, so this is a pair of enantiomers, and they have a mirror image. They're a mirror image of each other. Or we have diastereomers, right? In this case, we have two stereocenters that are one of them, and they are both on the same side. The other one, they're both on the opposite side. So enantiomers are non-superimposable mirror images that are difficult to separate, and diastereomers are any stereoisomer that is not an enantiomer. We have a couple other terms. The ER, or the enantiomer ratio, is going to be the ratio of a mixture of one to the other. A racemic mixture is going to have an enantiomer ratio of 1 to 1. And a diastereomer ratio is going to be the ratio of diastereomers in a mixture. Let's take a look at this graph. This figure is a